In the previous video, it is evident that assembling simple to moderately articulated models are a relatively straightforward task, provided the complexity of the construction remains low. By low, we refer to a small arrangement of bodies and joints. However, as complexity increases, the process becomes tedious and prone to errors. Some of the main challenges include, but are not limited to, the assembly process involves creating complex hierarchical chains of various component types, which must adhere to strict parent-child structures. This makes it easy to make mistakes. It is only suitable for handling static meshes parented to a rigid body node, as the Unreal Blueprint Editor lacks a way to provide detailed selection information about the skeletal mesh bone hierarchy. The Blueprint Editor cannot be extended by third-party applications. To address these limitations, we developed the Newton Asset tool, which provides users with a starting point by generating the necessary blueprint components. The Asset Editor offers several key benefits: supports skeletal meshes, enforces a consistent naming convention, maintains the parent-child hierarchy by creating partial joint parent chains, allows filtering when adding special constraint types, ensuring they are only applied in valid configurations. This is particularly important for contractions with closed kinematic loops. Limitations. Despite its advantages, the Newton Asset tool has some constraints. It is specifically designed to work with Unreal Engine skeletal meshes. The root node must be a dynamic rigid body that is movable. Few others that can be seen as inconvenient at the moment. In this video, we'll use the Newton Asset tool to create a simple industrial robot with 7 degrees of freedom. This serves as a foundational example of an inverse dynamics chain. Once you understand how to set up the structure, creating more complex robots becomes easier by repeating the same principles. Open the content browser and create a new folder to store your assets. Import the FBX file representing the visual robot mesh. Ensure the model is imported as a skeletal mesh. We are using a freely available mesh of a classic robot model, but you can use your own or create one using 3D modeling software like Blender or 3ds Max. Open the imported asset and inspect its hierarchy. If the bone orientations aren't correct, you may need to adjust them in your modeling software. In the content browser, right-click and create a new Newton Asset, Newton Model. Use a clear naming convention for easy identification. Double-click the newly created Newton Asset and open the Newton Editor. Select and assign the previously imported skeletal mesh. Close and reopen the editor to refresh the settings. The editor layout shows a physics tree panel with a root rigid body automatically assigned as the base, a skeletal tree panel with skeletal mesh bone hierarchy, and a detail panel to edit each node property. Click the R button on the physics tree toolbar to activate binding mode. The button to the right turns blue to indicate this mode is active. Start from the root rigid body and work downward. Click on each rigid body and assign the corresponding skeletal mesh bone. The physics tree panel and the details panel will update with the bone index, bone name, and default binding transform. Right-click on each rigid body and select the appropriate constraint. For an industrial robot, each of the 6 rotating joints should be represented by a hinge joint. Once a constraint is added, the editor automatically creates a child rigid body. Continue this process for all 6 arm segments. Then add 2 sliding joints to the last rigid body of the chain for the gripper. You can enable filters to hide bones and shapes to make the setup process easier. Click the R button again to exit bind mode. If needed, reset and adjust bindings. Right-click in the content browser and create a new actor blueprint. Open it in the Blueprint Editor. Add a Newton Model component. Select the model component and in the Details panel, assign the Newton Asset we just created. Click Regenerate Blueprint to auto-generate a hierarchy of rigid bodies, collisions, and joints. Compile the blueprint and save it. Place an instance of the robot in the scene for testing. Run the scene, and you notice that the robot falls through the floor. This happens because the rigid bodies have null collision shapes. To fix this, we go back to the asset editor and add collision shape to all rigid bodies. Select the gripper bodies and add a box collision shapes to each body. Resize and position them correctly. For each arm segment, use convex hulls for simplicity of physics representation. Recreate the blueprint hierarchy to apply these changes. The robot should now properly interact with the scene but will still behave like a ragdoll due to missing joint limits. Return to the Newton editor. Enable debug mode for better visualization. Adjust the limits for each joint. The gripper sliders should have appropriate movement constraints. The elbow joint has a limited range, so set limits accordingly. We also set the mass distribution of each body part. Since we don't have precise mass data, use common sense. Arm segments are lightweight, often hollow. The base is heavy, typically made of iron. Rebuild the blueprint and test again. The robot now moves with constraints, but still behaves like a ragdoll because hinges lack motor functionality. There are two ways to motorize the hinges. Forward dynamics. Each joint acts as a motor, trying to reach a target angle while affecting its child joints. Works well for predefined animations. Closed kinematic loop. Inverse dynamics. Calculates the torque for each joint based on the desired tip position. Uses rigid body dynamics instead of traditional inverse kinematics. More suitable for robotics and other mechanical simulations. In this demo, we'll use the inverse dynamics method. Go back to the Newton editor. Attach a 6-degree of freedom effector to the robot base. This effector controls 6 independent movements. The effector uses a proportional derivative motor. We set the strong spring damper to make very responsive. We limit the effector's power to 2 tons of force to prevent instability when grabbing objects. Select the effector target from the drop-down list of possible options. Adjust the target frame transform offset to set the robot's desired motion. Since the mesh isn't built to industry specs, minor misalignment is acceptable. Save. Rebuild the blueprint and test again. If the robot still behaves incorrectly, recheck gripper motorization. Fine-tune joint limits and mass values. Adjust the effector force. Repeat this process until the robot moves as expected. At this stage, we have a fully functional robotic arm with inverse dynamics control. However, we still need a way to control it interactively, which we'll cover in the next video. Thanks for watching.
See you next time.